Hello, welcome to the second lecture on the lecture series of GIS applications in forestry. Today, I want to continue to describe what GIS is all about. GIS can be described as a unique integration of computer hardware, software, peripherals, procedural techniques, organizational structure, and people for capturing, for manipulating, storing, analyzing, modulating, modeling, and displaying of geographically referenced data for solving complex health-related problems. Therefore, GIS comprises of hardware, software, and geographic data. All these technologies have been considered, they are part and parcel of GIS. We have the scanner, we have plotter, we have drone, we have map making devices, we have handheld GPSs, we have Android phone, we have iPad. All these are comprises can be regarded as GIS technologies. So geographic information system technologies. So when we say what is GIS? We can actually describe GIS as a unique integration of this. So that is a definition that is based on the components of GIS. So GIS components include the hardware, software, data, people, and methods. Hardware, software, data, people, and methods. Just as we have here, because we require people, which we usually refer to as wetware. That means hardware, software, and wetware, and then data. The wetware comprises of the method and procedural techniques to apply GIS in any context. So GIS comes in GIS software. The component of the software of GIS come in different types. We have some that are commercially available, that is proprietary software that need to be purchased. The license need to be purchased before we can have access. That one include the leading software is Esri product. Esri started with ArcView, ArcInfo, then ArcGIS 8 and ArcGIS 9, ArcGIS 10, and series of ArcGIS. The leading software, Environmental Scientific Research Institute, is the leading software vendor. Then we have the GeoMedia, we have MapInfo Professional, we have Global Mapper, we have Manifold GIS, we have Small World, which is used for electric mapping. We have Bentley Map, we have Map Viewer and Software, we have Idrisi. This one, the first 8 are what we regarded to as a basically vector-based GIS. And then we have the following ones that are mainly raster-based. We have Idrisi, we have EDAS Imagine, we have Envy, we have AutoCAD Map, we have Super GIS, we have Maptitude. All these ones are the commercially available software, or the software you need to procure license. You have to buy license to before you can have access to the use of the software. Then we have the freely available software, which we regard to as open source, or free software that you can download and you can use. The leader of this openly available GIS software is QGIS, Quantum GIS. And we have also OpenStreetMap, we have GRASS, we have Saga GIS, we have UDIG, we have Whitebox GAT, we have BAT Open Source, we have Orbis GIS, and we have OpenJump. These are the openly available or open source, free open source GIS software. You need to understand how you can implement your project in any of these. My advice is that you get used to one commercially available software and also one free or open source GIS software, because there are some projects that require the use of OpenGIS, especially when projects are sponsored by international agencies. They want to reduce the cost of implementation of the project as much as possible. So they always ask people or the implementer of their project to use open software so that they don't have to, the beneficiary of the project will not need to be renewing the license every year. Most of these software that are commercially available require the renewal of the licenses every year, and this may put a lot of burden on the beneficiary of the project. There are so many advantages of the open source GIS software, and we are just looking at an example of open source GIS software, which is Quantum GIS, and which we are going to use in the next few examples and exercises that we are going to carry out. QGIS is a free and open source GIS software and offer most of the functions that you can find in any of the commercially available GIS software. In fact, QGIS is rivaling or is competing favorably with in terms of the functions and the analytical context with what you can achieve also in ArcGIS. So we are going to concentrate on QGIS in this lecture. But ArcGIS also has its own advantages. ArcGIS has an advantage because there's a lot of customer service that ArcGIS can render. Once you obtain the GIS software from Esri, if you get the original license, you can actually have some support, customer support, which can be technical support when you encounter crisis or problems on the software. You also have a line chart and real-time chat with the customer support, but you have to rely on the community of users to get support for the QGIS, and sometimes it may not be forthcoming because it's at the discretion of the people at the other end, the community of users. So now we want to look at the types and models of data in GIS. GIS actually have two types of data, two categories of data, which we have mentioned in my first lecture, which are that spatial data or non-spatial data, or we call it spatial and aspatial data. We can call it geometric data or an attribute data. These are the two major types of data. But under these types of data, the spatial data can be captured in different models, which we call vector and raster. Vector data capture the data or record the data, the spatial data, as points, lines, and polygon, which we call cartographic primitives. Why do we call it cartographic primitives? Is that since the element, human being have discovered that you can actually represent anything on the surface of the earth as point, line, and polygon. While the raster form of representation use rows and column matrix of rows and column. You can see the real world is mapped, is produced as point, line, and polygon here, and then is produced as a series of rows and column matrix in the raster data capture. These are some of the examples of data in the vector models, spatial models. We have point data. The same data can be captured as points and can be captured as line, can be captured as polygon, or you can capture your space, your spatial data in form of a combined line, polygon, and point. Then we have different types of formats in which we can have GIS vector data types. Shapefile is actually the most dominant and the most popular vector data type, and shapefile is the generic file for Esri. Esri is the major producer or user of shapefile. But shapefile doesn't stand alone. It's also a collection of different other formats. We have the .shp, we have which contain the map data. We have the .shx, we have .sbx, we have .dbf. dbf is the one that captures the database, and then we have the shx, another one that captures different formats. Then we have the raster data and the vector. GIS uses two types of data to depict the art. In the format, we have the vector and raster data. And we have different form of things that you can represent with the vector and the raster data. And this is an example of this area can be represented as vector, and the same data can be represented as raster in this environment. So when we have the vector data, then we have the attached attribute data. When you have this is the spatial data, this is the attribute data. But the format of capturing this data in this context is vector. So you have the map of Nigeria local government with different polygons representing local government. And you now have the spatial data, the attribute data corresponding to each row corresponding to the spatial data. So each row is linked to a polygon, and that is raster, that's vector data. But in the case of raster data, we have what we have in aerial photographs or satellite images. They are actually raster data because pixels are used to represent uh, unique data spot, and then each of the pixel contain what we refer to as pixel values or refer to as data numbers or tonal values. These values represent different color code to the human eye, and which is used to represent different shapes and features. So this is an example of a raster mapping, and you can see that as you have this, each spot is represented by the color code that is assigned. Each cell is represented, each spot is represented by a cell, and the cell represents what is the value attached to it, and it can be the tone that is coming or reflectance properties of the point, of the data on that point, the feature that is located in that point. It can be the reflective properties, reflectance from that place, or it can just be a data assigned to represent that point. So we have rows and columns to represent, because each point or each pixel has its own row that contain the information about the data set. So when you have the raster data also contain both the spatial and the attribute. These are the two types of data we have there. So what we have here is the rows that correspond to each pixel, while just as you have the polygon of the local government being represented in the table that is attached to it. So we have these are the raster. So an example of raster data is drone image that we have here, and then we have this another data set. This is the attributes of the data set. This is the spatial data, all captured in the raster environment. So we also have an example. This feature can be represented as another example of real world, and then when you are capturing the raster environment, it is captured like this. And then if you are capturing using the vector representation of format, you capture it like this. In each case, you see because a map is a model of reality. It's a model of real world. So you have it in this way. Same thing, you can have river channel in the vector, which is line features. And then when you represent the same feature in raster environment, it is represented thus. The same thing is another example is given here, and then you can have different raster illustration. Thank you for listening, and I welcome you to subscribe to this channel so that you can get the next video. Thank you so much.